Welcome back, Patreons, and welcome to our last part of DC Circuits, a series we're currently in, learning fundamentals of electrical engineering, basically electronics principles concerning DC circuits. And in this last episode, we're going to take several things that we've learned and actually build ourselves a rather unique circuit. As a matter of fact, I'll zoom in on this right now, then afford you a few minutes to actually look at this diagram and write it out yourself. Now, if this circuit looks familiar, well, it's probably because you've seen it before. And basically, the icon for my channel, the little figure there, this is called an Astable multivibrator, and I'll talk about it in a second, but here's all the values you'll need. Now, we haven't used transistors in the past, but the transistors you're going to grab are some SS8050 NPN transistors. All of our resistors are quarter watt resistors. That's what we're going to grab. There goes the values: 470, 470, 47K, 47K, 470. Get yourself two light emitting diodes, preferably red. Then two 10 microfarad 25 volt caps if you have them, although our supply voltage is only going to be 9 volts. And then obviously two transistors, both NPN. And I'll stop for a second and say you have time to look at this diagram and write it yourself. Now, here we have the actual circuit built onto our breadboard. I'll zoom in for a minute so that way you can see it. But essentially, anything that needs to be on a positive rail, i.e. our resistors are going to the positive rail, and which will feed in our 9 volts from our power supply. And anything touching the negative rail, i.e. the emitter from both of our transistors, will go over here, touching our negative rail. And then we just make all the connection points in between, but you can see where we have this crossover here. What I did is I just used two jumper wires. And there will be a reason for that a little bit later on in our discussion. But this is essentially how you're going to set it up on your breadboard. Now, you can make yours look a little bit differently than mine, but so long as the connections are done in the same way, you should be fine, especially considering, you want to take note of your anode versus cathode of your LEDs. Okay? Now, what is an astable? That's probably the first question that you're asking. Well, the astable is a simple circuit consisting of at least two switching transistors, a cross-coupled feedback network, and two time delay capacitors. These two guys here. Okay. Which allows for an oscillation between our outputs. An astable is also sometimes referred to as a free running oscillator. Now, that being said, what would you typically use an astable for? Well, we'll see here in a second that it's used to generate square waves, which is very important in certain things like a computer system, because this can serve as a timing oscillator or a clock within your circuit. Okay. It can also be used for circuits that as in our application, to create flashing lights and supply electricity. So those are some of the tertiary functions. So obviously this circuit is going to have some pretty good application, and it's a very common circuit to learn when you're starting out in the electronics career field. As a matter of fact, 20 years ago, this was the very first circuit I built when I went through electronics principles. However, once it was explained, we were given cookie cutter, essentially PCBs, and we had to practice soldering components on it because it was in a soldering course in which we were evaluated on how well we soldered the components and kept to technical standards. But anyways, we've discussed many concepts or applications of several of these components within our DC circuit, such as resistors and capacitors, and a bit of diodes, or LED, light emitting diodes. We haven't really discussed the transistor though, and so I don't want you to be dismayed by that. So really, when you look at a transistor, let me set this aside for a second. And you're probably at least aware that some are called NPN and others are called PNP, right? Well, that's just basically identifying the junction points, okay? So really, when you're looking at a transistor, you can put it into the perspective of diodes, right? So on a diode, you would have an anode, right, and a cathode side, right? So here would be the positive side, and here would be the negative side, or the P junction and the N junction, right? Well, let's think about this concerning a transistor. We'll first discuss the PNP. So I'm going to draw it out here. Positive right here, right? Cathodes here, so this is our negative junction point. Let's make another negative junction point here with another cathode and an anode of a diode here. And there you have it. So really, when it's concerning transistors, a PNP is basically two diodes where the cathodes are meeting in the center. As a matter of fact, if I were to draw a line down this way and out this way, we could say positive, negative, positive. And if we were to look at it simply by its junction points, P, N, P, okay, with the base needing the negative, and then the emitter and collector requiring that positive input, okay? It's pretty simple, right? This is your basic PNP. Well, what about NPN? Well, that's pretty much the reverse of what we've just done. So let's draw it out. Let's take cathode to anode, and we need our anodes to be co-joined in the center. And there we have it, N, P, N. In the same fashion, let's write it out as our junction points, N, P, N. So basically, we need a negative potential on our base in order for an NPN, or excuse me, a positive potential on our base for an NPN to bias, versus a ground on our base here, or negative, or in some applications even a reverse voltage is what I was about to say, but an inverse voltage is basically a voltage where its polarity is a DC voltage where its polarity is inverse, so say negative 5 volts or something like that. But anyways, moving on, emitter and collector, elector, there you go. Freudian slip there. I was thinking collector while writing emitter and said elector. Well, that's the basics of a transistor. So nothing really too overwhelming here, and you can kind of look at them in the sense of you would in a diode or two diodes, where either their cathodes are conjoined at a meeting point, such as with our PNP, or the anodes are conjoined at a node or meeting point, such as our NPN. That's basically all a transistor is. Okay. Let me set this aside. All right. So again, here is our schematic, and here is it over on our breadboard. Now, primarily concerning this this astable multivibrator or free running oscillator, I want to point out a couple things for you. Primarily, first thing is these 470 ohm resistors are basically there for current limiting to our diodes, okay, to provide us a voltage drop, because we don't want the full 9 volts presented at the cathode, or excuse me, the anode. Now, these are 2 LED diodes, meaning that they require something like what, a 1.8 forward biasing voltage or something like that. Hold on a second, let me pull them and we'll actually look at the package. Here we go. Yeah, they require about a 1.8 to 2 volt forward biasing voltage. And they're also going to drop about 2 volts across the LED heading, within our circuit. But there we go. There goes the basics of these LEDs. So we want to see most of that 9 volts dropped off at, being dissipated by this resistor as heat and supplying essentially 2 volts going to the LED. And we'll do the math here in a second, along with the demonstration. Well, first off, I would ask, do we need to consider all these resistors if we need to determine how much we have our voltage source? We know it's going to be 9 volts. How much current is going to be drawn through the circuit? Well, let's do a quick demonstration of our astable. As you're watching it, are both LEDs on at the same time? If you said no, you're obviously right. That means that as this thing is free running or oscillating, that essentially the only resistors we're concerned about are whatever resistors correspond to whatever output is turned on, okay? So let's think about this for a second. I have a 9 volt input. I'll grab a piece of paper here. Well, let's think about Ohm's law for a second. Voltage equals I, our current, times R. But we need to solve for our current, right? So another way to write this would be current equals voltage divided by R. Okay. That's principle 1 that we've learned was Ohm's law over the past several videos. Right now we don't know what our current is, but we do know what our voltage is, and we do know that, well, that these outputs oscillate turning on and off. So really, you only need one output. Let's take this one here. Okay. There we go. I pulled out one side so it can no longer oscillate, and we've essentially set up our circuit. Now, by removing this out of the equation, we can follow our input voltage and kind of look at this and determine what is biasing this transistor here to cause this diode here to turn on. Well, we see the voltage applied through this 470k ohm resistor to the base of this transistor. Okay. Now, I'm not concerned about this capacitor here right now. But anyways, I can look at this resistor over here. Well, essentially, we know that this is a parallel resistor circuit. When we look at it, these resistors are not in series. So how do we do a current calculation? Well, if you recall from our video series, our P as our total resistance is going to, for parallel resistors, it's going to equal R1 times R2 over R1 plus R2. And if we were to multiply 47K by 470, we would essentially get 22,090, this value here. And then if we were at the bottom, our value would essentially be 47,470. Which is going to give us a total resistance of, what? Let's do some quick math. 22,090, 000 divided by 47,470 equals 465.3465. And then it just starts repeating, but that is our total resistance. Okay. So if this is our total resistance, then I must equal 9 divided by 465.3465. All right. 9 divided by 465.3465 equals 0.019 amps, or we could express it as 19 milliamps. Now, I expect to see 19 milliamps over on our circuit here, if we were to measure it. Now, I don't know if this is coming across, but my power supply is showing 23 milliamp draw. But I suspect if I was to take my voltmeter and hook it up to here, it's actually going to be a bit lower than that. And that's because we have a lot more things in circuit that we're not considering, in which our current is being divided, and there will be another voltage drop across our LEDs and etc. So let's hook this back in. Okay. Now, because we learned how to use our multimeter, right? I'm going to do a current measurement in DC. And then what I'm going to do, positive lead to here. And let's put my negative lead to here. There's actually going to be more resistance in the circuit simply because of our wires and stuff. It's going to add to our resistance. But we can see that we're actually drawing about 15, 16 milliamps. Okay. So we know, set this aside, that our true amperage of the circuit, I, equals 15 milliamps. Okay. Calculating wise, we were close, but like I said, we didn't do the entire circuit with all the components on here. And we're not going to, because this is just basic foundation type stuff. But that gets us close. And with either one of these, I could actually use either one to determine our power for the circuit, okay? Now, if you recall power equals V times I, or voltage times current. Okay? So if our volts is 9, and our current is 15 milliamps, well, what is going to be our power? Or is our voltage is 9 and our current is 19 milliamps? We'll look at both, and we can determine our power. So 9 times 0.015 That's coming to what? 0.135 watts. Or we can do 9 times 0.019. That comes out to 0.171 watts. So way less than a quarter of a watt. Of course, a quarter of a watt would be 250 milliwatts, or 0.250, right? Well, why do we need to know that measurement? Well, remember I said all of our resistors are quarter watt. So there you go. There it is in the application, and we know that we would need resistors that were at least with a power rating of a quarter watt. Could you go above, use half watt or 1 watt resistors? Sure, but given the cost of the difference between, you could just stick with a quarter watt resistor and be perfectly fine. So we've determined our, what power rating we need for our resistors in circuit. What about the actual voltage drop, as I mentioned? Well, let's think about that. If we're seeing, actually, let me disconnect this and we'll come back. All right, we normalized everything. And got my multimeter set back up to do a voltage measurement. We're seeing 9 volts here. What are we seeing right here? Look, it's kind of jumping around on us, isn't it? Let's eliminate 1/2 of the circuit. There we go. Now we got a constant state here. Well, let's do our voltage drop calculation. And that should be pretty easy, because I times R is going to give us our voltage, right? So if we know our circuit is 0.015 amps, or 15 milliamps, and our resistor here is 470 ohms, and again we can do some math, and we could say 470 times 0.015, we should see a voltage drop of approximately 7 volts across this resistor. Let's check it. Yeah, we're just about there. Well, 9 minus 7 is what? 2? What do we need for this resistor? 1.8 to 2? Which means that we are left with 2 volts to bias that resistor. Now let's check to see what's applied to the resistor. Not the resistor, the LED. Excuse me. There you go. 2.1 volts DC. So, with this resistor, we've now determined, and of course you would swap out these resistors depending on the LEDs you were using, but there goes how you determine how much voltage drop you need in order for your LED to be biased, for current to come through, and for it to start producing light for us. That being said, I also want to bring into focus, well, we need to have a voltage drop in order to not burn out our LEDs. What about our transistors? Now, you might have heard me mention this on my YouTube channel, but yes, your transistors, you do have a concern at your base, a max voltage in order to bias them. They are current sensitive devices, unlike older technology like vacuum tubes. Now, some are more sensitive to current than others, depending upon the type of transistor and, the application and circuit. But essentially, yes, we need to be concerned about this, and I'll show you an example as to why. Okay, I've pulled up the data sheet on the SS8050 NPN transistor, as you see right here. And let's scroll down and look at something here. I want to look at the base emitter on voltage. And we see that our max on voltage is, what does it show? 1 volt. Well, if we look at our diagram, we can see that coming through here, we hit that 47K resistor going to the base of our transistor here. And if you're doing the math, you'd probably say, man, 47K, that's way more that's needed than to drop the 1 volt. Well, there are other things that you need to consider that we won't go into here, but this is going to severely limit the current, and we're still going to see a slight voltage. As a matter of fact, we can see 0.75 volts right here being applied to the base of our transistor. Now, could I go with a lower resistor value here? I absolutely could, but when we check our current, say from this side of our resistor to over here, if I was to remove it out of circuit, you would see that that current would be substantially higher. As a matter of fact, why don't we just check the current now with that 47,000 ohm resistor. Pull it out here, put it here. We'll go down to a current measurement, and I can essentially remove this. Okay, up. And we'll just touch between here and here. LED should come back on. You see the current so low that my multimeter can't even pick up on it. So we're talking about a very efficient circuit that's not really going to burn out this transistor too quickly. And go back up to voltage. All right. 0.7 volts, is that greater than the 1 volt that we have here for our transistor? Nope. So we are below the maximum threshold for biasing this transistor. Again, different applications would call for different things, but this is why we experiment, why this is such a good circuit to experiment on. You swap out your LEDs, you swap out your resistors, you do your math as best as possible, and then you test with your bench multimeter or handheld multimeter. And now we have this astable and normalized, and what I've gone ahead and done is I have coupled 2 probes going to my oscilloscope, and as for right now I only have channel 1 turned on. But you can see that the voltage has been set to 2 volts per division, and our span is at 250 milliseconds. And we got that nice square wave being developed, and we can see it's generating a frequency of 1.47 hertz. Yep, it's pretty low frequency. It's not too high at all, to be honest. But I want to annotate something. You see how it's a bit rounded right here on this edge, but it's directly cut off here. Well, that's primarily due to the capacitor charging at the beginning of its charge before it starts to discharge again, and our voltage drops. Essentially, as I previously mentioned, the capacitor is what controls the oscillation of the circuit. And the value of the capacitor, i.e. the voltage, is important because we don't want to use a capacitor whose voltage rating is too low for the actual circuit, 9-volt circuit. So, we're using a 10 microfarad 25-volt capacitor. The actual microfarad rating and the characteristics of how quickly it takes to charge and discharge is what's generating essentially our frequency and this oscillation that we have occurring here. Now, like I said, I only have one channel turned on, but if we turn on channel 2, and there we go. And we can essentially see right here that when channel 1 is on, channel 2 is off, and when channel 2 is on, channel 1 is off. And they're both generating the same frequency. And like I said, with application, you might need to use an Astable as a clock within computing systems. It's pretty traditional use. Maybe you need to use this as an oscillator inside of some type of radio circuit, or maybe even think of it like this. As many of y'all saw the digital handheld pets that I refurbished, and they made use of an oscillator up in the, I think, kilohertz range or maybe megahertz range. Again, this is the principle that we abide by concerning that. Now, like I mentioned, the 470 ohm resistors were selected based upon the voltage drop required for these LEDs, right? Now, you could swap them out with a different resistor, so long as you're not over voltaging the collector side or presenting too high of voltage to your collector, or allowing too much amperage through collector to emitter and burning out your transistor. So for demonstration purposes, let's remove the LED from the circuit, and you can see that essentially only channel 1 is now on. And let's jump over our 470 ohm resistor where the LED was jumpered on over to. All right, you can see we don't have as much voltage drop there on channel 2 because essentially, we also have a small voltage drop with the LED. Well, can we do the same to the other side as well? Pretty sure we can. Doesn't look like our frequency has changed much. We're still around 1.4 to 1.5, but they're kind of stepping on each other. Wonder what happens when I turn channel 1 off. Yeah, a slight change in our frequency, but not by much. Let's remove this LED. Okay. Let's jump over this resistor. There you have it. So there you go. Depending on your application, what you could do is eliminate your LEDs and just use your resistors at whatever value is going to satisfy voltage and current maximum requirements for your transistor. Now that I've got everything nominalized back together the way it was before, if you recall me stating the capacitance value of our capacitors, right, is going to have effect on our timing. So we are using currently 10 microfarad capacitors. Now, to make this a little bit easier, what I'm going to do is uncouple our probes Then we're going to our SIGGEN. Okay. And this will allow me to swap around capacitors a little bit easier. But let's see what change we get just by making one change. Now I'm going to go from, say, 10 microfarad. We can go, let's do 100 microfarad 16 volt. That's still higher than the 9 volts of our circuit. So we should be able to do a change there. Or we could do an even more significant change here with the 1000 microfarad 16 volt caps. Why don't we, well, those are pretty big. Why don't we stick to the 100 microfarad cap? So there goes 100 microfarad. There goes 2 100 microfarad. Set this aside. And we need to also keep in mind our polarity of our electrolytics that way and how it is in circuit. I realize I've got a lot of things jumbled right here on top of each other. But we'll go ahead and swap out our capacitor. So what I'd like to do is try to pre-bend the leads just a little bit to make life a tad bit easier for myself. Yeah, just a little bend like that. Try to get the legs even, and then we can position better from there. But let me pull out this cap. And look, they're both on. So now we only have one capacitor in circuit. Okay. And our negative rail needs to go to the 47K resistor. Positive rail to the other, to the cathode of the diode. So should be able to do something like this. Now we can see that one stays on a lot longer than the other one. And if we were to take that one out, now let's put this one in. Oh, come on. There we go. We can see our switching is now taking longer, so I can imagine a pretty significant change in frequency. Well, I've given this some time to go through several cycles, and we can see that at least by the oscilloscope, it's giving us a frequency of 0.15 hertz. So yeah, our frequency is drastically reduced as we increase capacitance. Well, what about if we drop capacitance? Well, this time I've elected to go with a 0.47 microfarad cap rated for 50 volts. And as you can see up on our oscilloscope, our frequency has increased to 36 hertz. Corresponding to that, you can see that our LEDs are flashing a lot quicker. Now, to be honest, what I perceive in my eyes here, these LEDs are flashing a lot quicker than what you're seeing on the screen. And that's primarily due to the refresh rate of our video recording, you know, how many frames per second it's able to capture. These are flashing at a rate a lot more rapidly than what the camera can capture. Now I can perceive the difference with my eye, but if you do this versus what it's actually showing, because it looks slower under recording than what it does to what I can perceive with my eyes. Definitely a lot faster. But anyways, you'll notice the same thing if you're following along in this video. But we can see that difference right there. Which brings up another question. And that question is, why am I using electrolytics? Well, really depending on your circuit and the application, these electrolytics are going to give you a lot more stability based upon ambient things that are occurring, such as heat, etc. So maybe we can demonstrate something here, or at least try. Now, I don't know the actual voltage rating of these capacitors here. They are not truly designed for this kind of circuit. They're not, polarized. It's not designed for a DC circuit such as this. But this is still a 47 microfarad capacitor, or 0.47 microfarad capacitor. So I want to uncouple my leads for a second. Okay. And perhaps we can use this in circuit instead, though it's going to be, I think, pretty hard to reach between a couple things, but we'll try it. So I'm going to pull out this 47 or 0.47 microfarad cap. We're going to try to insert this one instead. These just might not be long enough. There we go. We got it in there. All right, and again, let's hook things back up. And we're still pretty close to the frequency we were before. I wonder what happens as I put my finger around this capacitor. I'm taking it off. Did you see how that frequency changed ever so slightly? 34.79 hertz. Now let me touch it and warm it up. Now it's increased there to 34.8482. Now I'm going to let go. Yeah, we can see it's cooling off and that frequency is dropping down there a little bit. Let me pull it out. And we'll put this other one back in. And hook this back up. All right. Now looking at our electrolytic, 36.2. Let me put my finger on it. And let me take my finger back off. Did y'all notice a difference? Well, I sure didn't see any difference this go around. However, when we put this capacitor in there, my body temperature when my fingers are touching it, my body temperature has an effect on its value, okay, on what is occurring. And so capacitor selection, depending upon your circuit and circuit design, the type of capacitor is also extremely important. If you're looking for something with a lot of stability and ambient temperature not having an effect on it, then you wouldn't want to use something like this within your circuit. You would want to use an electrolytic. Now, as I mentioned, and we just demonstrated, our capacitor is going to have an effect on our frequency. But what I haven't mentioned is this resistor will equally have an effect on our frequency. So like I said, we primarily selected these resistors for the LEDs, but let's pull out our LEDs to eliminate them. Okay. And let's put this resistor over. And this one as well. All right, we have our clock back. And what we're going to do is we're probably just going to play with this resistor here. So let me turn off channel 1. Okay, and we'll bring channel 2 into here. We see channel 2. All right, and we're generating a clock frequency of 31.1 hertz. Why don't we change out our resistor value? This is currently a 470 ohm resistor. Let's pull it out. And let's get a resistor of a much higher value. Let's see, what do we have here? 47K, 56K. Let's go with a 220K ohm resistor. It's in the very back of here. If I can get this thing open. And we'll take out one resistor out of the bag. There we go. And we need to make that same connection as what was previously made. So put in the positive lead. And do I have that in there? I think that's in there. Well, that value might be a bit too high for our circuit. So let's go with a different value. Okay, so what I've chosen to do in this instance is swap out our 470 ohm resistors for 1.5 k ohm resistors, and you can see that corresponding frequency change right there on the oscilloscope, because we're now reading 30.98 hertz. And if I add back in channel 1, there we go. So, capacitor value is important, as well as a resistor value. Now, if you wanted to drive this with LEDs, that resistor is going to be very important for what you're driving concerning a voltage, right? But if we're just using this to generate a clock frequency, we have to be concerned about our capacitor and our resistor, and the combination of those two things. So like I said, by all means, this is a very common circuit that you can build and you can experiment with. Now, if there are some things I would recommend, I'd probably go up to half watt resistors instead of quarter watt, because it's just easier to move them around your board. Now, you saw me multiple times and I never removed my rings, so bad on me. Disconnecting things with power applied. I don't recommend doing that. I should have forewarned, if you're following this, you're doing so at your own risk. If you're swapping out components, I would recommend disconnecting your positive lead first, okay? Then making those corresponding changes. Like I said, I have formed some very bad habits over the year, and there's not enough current and not a significant voltage in this circuit for me to be overly concerned, but at the same point in time, if you're a novice, you should be. But this is your Astable, and it's got a wide range of applications, like I mentioned, and is a very good first circuit to build within your own lab, and something for you to play around with. So all that being said, this is going to do it for our DC circuit series. And most likely I'll start up on, fundamentals of AC circuits next. I might do one TMD video prior to that, primarily with my signal generator. But please let me know if you appreciated this training, and hopefully you enjoyed following along with me in building your own Astable multivibrator. And you can see the potential application for such a device within the scope of mini electronics. So that being said, if you've enjoyed this, let me know here on Patreon by hitting that heart little doobly-doo thing and commenting in the comment section. Thank you for watching. Take care and goodbye.
Mark?